All right, let's jump straight into this explainer. Today, we're going to completely demystify the core components of atomic structure and give you the absolute foundational tools you need to master chemistry calculations. Whether we're talking about a simple, single hydrogen atom or some massively complex biological molecule, the whole shebang comes down to the fundamental rules governing what's going on inside the atom. We're going to break it all down step by step.
Here is our game plan for today. First, we'll meet the subatomic particles, then define atomic and mass numbers. After that, we'll calculate atomic components, dive into variations like isotopes and isobars, and finally, calculate atomic mass. Let's get right to it.
Section 1. Meet the subatomic particles.
To really understand the atom, we have to look at the absolute smallest scale and meet our three main characters. Protons and neutrons, those are your heavyweights. They carry almost identical mass, right around 1.67 times 10 to the negative 27th kilograms. But then, look at the electron. Its mass is so incredibly tiny, we're talking 9.1 times 10 to the negative 31st kilograms, that for our calculations, it's essentially weightless. But what it lacks in mass, it completely makes up for in charge, perfectly balancing the proton's positive charge with a -1. And the neutron, as the name implies, carries zero charge.
Moving on to Section 2, atomic and mass numbers.
Now that we know our players, how do they actually give an atom its identity? Well, you can think of the atomic number, which we denote with the letter Z, as the atom's unchangeable, non-negotiable ID card. If you know the number of protons, you know exactly what element you're dealing with. On the flip side, the mass number, denoted by A, literally just tells us how much stuff is packed inside the nucleus. Since electrons basically weigh nothing, your mass number is simply the total count of your heavyweights, the protons plus the neutrons.
Whenever you see a chemical symbol, it's basically a neat little visual puzzle. The element symbol goes right in the middle. The mass number, A, sits up top representing the total weight, and the atomic number, Z, anchors the bottom to give you your proton count. And here is a super quick trick. If you ever need to find the number of neutrons, you just subtract the bottom number from the top number. A minus Z gives you your neutrons. It's so elegant, right?
Section 3. Calculating atomic components.
Okay, here's where it gets really practical. When you're calculating these components, remember that your protons are your fixed identity. You can't change those without changing the element itself. Electrons, however, act like negotiable currency. You can add or subtract them depending on an ion's charge. In a totally neutral atom, protons equal electrons. But if you see a positive charge, the atom lost some negative electrons. If you see a negative charge, it gains some. Just do the opposite of the charge to your base proton count, and boom, you have your current electrons.
Let's actually look at this in practice. Take a neutral helium atom and compare it to ions like sodium and aluminum. Notice how the proton count stays rigidly exactly the same, while the electron count fluctuates to create that net charge. For example, look at the aluminum 3+ ion. Its atomic number is 13, which means it has 13 protons. But because it's rocking a 3+ charge, it clearly lost 3 electrons. So 13 minus 3 equals exactly 10 electrons. Once you know the rules, it's literally just simple arithmetic.
Let's test this out with a beast of a real-world application. Can we decode the formula and add up every single proton ID hidden inside a complex molecule like ammonium phosphate? The formula is NH4 taken 3 times PO4. All we do is find the atomic number, the proton count, for each element and multiply. Nitrogen brings 7 protons, and the 4 hydrogens bring 4. That's 11 inside the parentheses. Multiply that by 3, you get 33. Then add the 15 protons from phosphorus and the 32 protons from the 4 oxygens. Add all of that up, and you get exactly 80 protons in one single molecule.
Section 4. Isotopes, isobars, and more.
Now, things get kind of tricky because atoms have these relatives that sound incredibly similar but follow vastly different rules. The prefix iso literally just means same. So these categories tell us what particle stays the same across different atoms. Before we dive into the main 3, look at the bottom one, isotones. Those are just atoms that happen to share the exact same number of neutrons. Okay, let's break the others down.
Think of isotopes as having the exact same elemental identity, but carrying a little extra baggage in the form of varying neutron counts. Because they have the exact same number of protons, their chemical properties are completely identical. But because they have a different mass, their physical properties can change. Carbon-12 and carbon-14 are perfect examples here. They are both absolutely carbon, but one is just a bit heavier.
Isobars, on the other hand, are completely different chemical elements. They have totally different IDs, but they just so happen to weigh the exact same amount on a scale. Look at argon-40 and calcium-40. Argon has 18 protons, calcium has 20. Completely different elements, right? But because their total protons plus neutrons happen to equal exactly 40 for both of them, they are isobars.
Now, isoelectronic species are absolutely fascinating. They prove that totally different elements can actually mimic each other by gaining or losing just the right amount of that electron currency to match perfectly. Remember how an ion's charge changes its electron count? If different ions adjust their electrons to reach the exact same total number, they belong to this highly exclusive club.
This lineup is such a great example. Look at how nitrogen, oxygen, fluorine, and neon all hit that magic number of exactly 10 electrons, despite being entirely different elements. Nitrogen starts with 7 and gains 3. Oxygen starts with 8 and gains 2. Fluorine starts with 9 and gains 1. Neon just naturally has 10. And even positive ions like sodium and magnesium lose electrons to drop down to that exact same number, 10. It is just perfect chemical alignment. Our final stretch, Section 5, Calculating Atomic Mass.
We've mapped out the entire atom, so how do we weigh it? Because we know electrons weigh practically nothing, we can safely ignore them. We just count our heavy nucleons, the protons and the neutrons, to find our atomic mass in atomic mass units, or AMU. 1 AMU is essentially the weight of one single proton or one single neutron. So the formula is beautifully straightforward. Just take your mass number, and that is your atomic mass in AMU. But, nature isn't always perfectly neat. That's why we have to use a weighted average. We have to account for the fact that an element naturally exists as a messy mixture of various heavy and light isotopes out in the wild. If you scooped up a handful of an element from the Earth, you wouldn't get just one clean isotope. You'd get a specific percentage blend.
Take chlorine, for example. If you blend roughly 75% of the lighter chlorine-35 with 25% of the heavier chlorine-37, you arrive at the classic decimal weight of 35.5. You literally just multiply the mass by its natural abundance percentage, add them together, and divide by 100. This is exactly why you see all those tricky decimal numbers on the periodic table. It's just nature's weighted average.
Okay, before we wrap up today, I want to leave you with a really provocative thought experiment that completely turns everything we just learned upside down. Think about this. How much would carbon-12 weigh if we suddenly change the fundamental mass of the particles inside it? Let's say the neutron mass magically halved. Those 6 neutrons in carbon would only contribute 3 units of mass now. The 6 protons still contribute 6. And what if we doubled the electron mass? Well, that's a trick question. Even doubled, electrons are still practically weightless compared to nucleons. So your new mass would be 6 from the protons plus 3 from the neutrons, giving us 9. The overall atomic mass drops significantly. It really makes you appreciate just how delicately balanced the atomic world is, doesn't it? Keep questioning those fundamental rules, and I'll catch you in the next explainer.